our technology, RokiSafe, applied to Elasticsearch. So a little bit about me. So as Faith mentioned, so I'm the CTO at Aroki System, one of the co-founders. I'm also the co-director of the Encrypted Systems Lab and the visiting scientist at Brown University. I did my PhD in computer science and in crypto in particular, with the focus on encrypted search. And some of my open source projects and my projects in general are PicSec, which is an end-to-end encrypted photo app, and Clusion, which is an open source encrypted search Java library. And just as Faith mentioned, please, if you have any questions, any remark or observation, just please ask the question. Be happy to answer it. Yeah, so this slide is pretty almost standard, as you may heard in the news. Every month or so, you hear a new data breach impacting users' personal information. There are just a couple of them mentioned in the slide, but there are so many. Target was one of them, Equifax, Marriott, and just this slide is gathering more than hundreds of millions of records that have been disclosed to the public. And it's touching not only companies, it's touching governmental agencies, it's touching personal individuals. Everybody is actually prone to being to have his or her data disclosed. So this slide is interesting. So you may wonder what this number is about. So this 14 billion, I guess, records. These are the number of records that have been disclosed in 2019. And if you are also wondering what this 4% is about, this is actually the percentage of records that are being encrypted. What it means is that 96% of all of the records that have been disclosed, they are in plain text. So an adversary can easily read or extract the information that the record holds. So why is this all happening? And this is a valid question that you may ask yourself. This is partly because of the following architecture. So most applications, they communicate through the network with the server. And the server in a simple form is composed of a memory and a disk. So from a security perspective, what we have currently is we know how to pretty much secure very well the network, meaning that the communication between the app and the memory. And we know also how to secure the disk. But one point which is still vulnerable is the memory. So the memory is very, very hard to secure. So what you end up having is this form of architecture when the adversary cannot really see what's in the network, cannot really see what's in the disk, but can really see easily what's in the memory. So this is not really ideal because you give a pretty large surface of attack to an adversary. And we will get into more into that later on. We'll discuss end-to-end encryption in this slide. Sorry. So end-to-end encryption is this new paradigm that will allow you not only to encrypt the network and the disk, but have everything encrypted from end to end. And this is why we call it end-to-end encryption. Meaning that when the data or any request or update that leaves your app, it will be encrypted and the server will only operate on encrypted data. And the only entity actually that can decrypt the data is the application. So what ends up happening is the adversary only can observe encrypted data. And encrypted data, for those who are unfamiliar with encryption is that mechanism that makes everything looks like gibberish, which provides, of course, like confidentiality guarantees. So end-to-end encryption is that paradigm that will give you the ability to operate on encrypted data. So even if there is a data breach now, if you can observe it on the server, either on the memory, on the disk, or in the network, an adversary cannot really do anything with the data because the data is encrypted all the time. So what are the benefits actually of end-to-end encryption? And you can already guess part of it, especially regarding data breaches, but there are more to it from a company or from a business perspective. So when you store your data encrypted on the disk or in the memory, you have this ability that we call separation of duties. Separation of duties is this really nice feature that will allow you to pack your data encrypted on disk or in memory. And sysadmins and database admin can always be able to operate on data without seeing its content. So even if the data is encrypted, you have, the sysadmin have zero ability to see what's inside. But on the other hand, they still be able to operate on it, like migrate it, see the performance, evaluate it, and so on and so forth. And which is really actually what the job is about, not really seeing what the data contains, but actually being able to manage tables, to manage indices, to manage anything related to the database, but not the content. So this is one advantage of the separation of duty. The other one is that now companies can have more faith in the process of outsourcing the data. So imagine that you have very sensitive data and you want to outsource it to the cloud. So one worry that you may have is that the cloud can be compromised. The cloud can have, malicious employees and so on and so forth. So you can have different types of adversaries. So having end-to-end encryption will allow you to have this setting where the data is encrypted end-to-end. So you put your data encrypted on the server, you outsource it, whatever the cloud provider you will pick, the data will be always encrypted, which is really interesting. The second interesting feature of end-to-end encryption as well is data breach resistance. So this is something that I touched on in the previous slide. And basically, even if your data is breached, let's say that you encrypt your data, you put it on the server, even if the server gets compromised at some point in time, the adversary can only see encrypted data, gibberish, noise. The adversary can actually do nothing with the data. While currently, with the current systems and architecture, if there is a compromise in a third-party hosting provider or even in premise sometimes, so if there is a breach, the entire content of your data will be disclosed. Of course, this minimizes economic losses. There was this interesting IBM's 2019 cost reports on data breaches that actually emphasized the cost per breach, which was around 8 million, which is non-trivial amount. And finally, and actually one of the other most important feature of end-to-end encryption is by design, it will provide this ability to be compliant with regulatories, like GDPR, CCPA, and many more that are going to come because we as a society, we are looking to safeguard users' privacy. So having end-to-end encryption will just check the box right away because you provide confidentiality end-to-end. So how about Elasticsearch in particular? So Elasticsearch, last time I checked the last version, it provides the following. So it provides TLS, which is the network kind of encryption, which provides security, between the app and the server. So an adversary who's, spoofing or, getting some packets from the network, everything is encrypted, so they cannot extract any type of information. Elasticsearch also provide, but not enforced, disk encryption. It's also known as encryption at rest. It has also other name like full disk encryption and so on and so forth. And this provides, some kind of guarantees, but it's kind of still minimal in the sense that you will rarely see somebody who's breaking into the premise and, stealing a rack of servers. This is really very unlikely to happen, but still it provides some types of security guarantees. But Elasticsearch doesn't provide encryption in memory. So what it means is that when you use Elasticsearch to store indices, if you use, for example, third party to host, for example, your data, like the third party will be always able to see the content of your data. And even if the third party is trusted in some sense, you don't have any guarantees in terms of compromises. Like if the third party is being compromised, the data can be disclosed. So as we speak right now, Elasticsearch provides this kind of like two dimensions of security, but leaves the memory in plain text. So the adversary, of course, as we talked about in the previous slides, it can read what's in the memory. So one question, okay, so we talked about these paradigms, we talked about the current architectures. The question now, is it even feasible to have end-to-end encryption? You know, especially for Elasticsearch, Elasticsearch has so many properties, like it can perform search operation, it can perform update operation, it can perform some computation on the data. Can we even do computation on encrypted data? And this is something that I will discuss about in the next slides. So, but let's start with end-to-end encryption. So end-to-end encryption is possible. It has been implemented in so many places. So one of them, which might be the audience be familiar with, it's the messaging and the video. So messaging, actually, like WhatsApp, Signal, Messenger, all of these apps, they provide what we call end-to-end encryption. What it means is that when you communicate with your friends, when you communicate with your family, everything is end-to-end encryption. So the service provider, like Facebook or Signal, don't see, for example, what is in the data, what you are talking, what you are sending. This has been also implemented in video, like FaceTime and Skype. It has been also implemented in emails, and this is something that is coming more and more, like Virtue, Proton Mail, and also in archival, like Keybase. So, but these are services that we can consider, okay, simple services. They just do one thing, which is like sending the data. There is no computation on the data. So it's a valid question to ask, okay, I agree, you know, end-to-end encryption is possible on these services, but how about databases? Databases are super complex. You do so much more than just sending data. So the answer is yes. Actually, some database companies, they have already started the deployment of end-to-end encryption. One of them is MongoDB, that uses deterministic encryption and PPE, and this is something that we will discuss also about in the following slides. And there is also Microsoft SQL Server, like a couple of years ago, that they provided what we call always encrypted, that also use deterministic encryption and some form of trusted hardware, even if that trusted hardware I put into parentheses, that it's not really end-to-end encryption. I won't discuss this now, but I'll be happy to answer questions about that. Okay, the question now, okay, how do we query encrypted data? How can we use a database that can operate on encrypted data? And this is a question that we researchers and cryptographers, we have been investigating for so many years. One of the co-founders, Sini Kamara, has been working on this area for almost 2 decades. And myself, when I was doing my PhD almost 10 years ago now, we were working on it, and many other researchers as well. So solving end-to-end encryption, or having the ability to perform queries on encrypted data, can be solved using different primitives. And this is the slide just to give you an idea about what's going on from a research perspective. So you can solve it using PPE, or called property preserving encryption, functional encryption, structured encryption. You might have heard already of FHE, or fully homomorphic encryption, and oblivious RAM. So these primitives, they offer different trade-offs between performance, functionality, and security. And this is very important when you want to deploy something in practice and in real world. Actually, these 3 dimensions, they should actually be taken seriously, each of them. So this is kind of the evolution of where we are from a research perspective. In terms of property preserving encryption, the first research work started around 2006, that introduced deterministic encryption. There is order preserving encryption. I won't get into the details, but the one thing that I want to stress here is the yellow, kind of the orangey kind of text. So between the research introduction and the first deployment of Microsoft Always Encrypted, almost 9 years. And there are so many constructions and so many attacks around PPE as well. I will talk about security in the next slides. There is also oblivious RAM. I will not get into that. And there is a final structured encryption, which is one of the primitives that provide kind of like one of the best balances between security, efficiency, and functionality. And there are also designs, cryptanalytical studies, systems as well, and so on and so forth. So yes, so this is the slide that is kind of like interesting, that kind of like compare between 3 of these 5 or 6 primitives that we have talked about. So on the left side, you have property preserving encryptions, or PPE. So if you look at it as a kind of a 3-dimensional graphic, it is really good when it comes to performance and query strength. But in terms of security, is not great at all. Like it has been shown, and our co-founder actually like has written a paper about how we can break security very easily of PPE-based encrypted databases. So it's good, but not perfect. And especially from security, it's one of the aspects that we are really looking forward to achieve. It's kind of like not great. Second, you have FHE, which is great when it comes to security and query strength. Query strength means here expressiveness and functionality, like how many complex queries they can support. And FHE is also great. They can support really a lot of queries and a lot of database queries, but it's really bad when it comes to performance, and it doesn't compare at all positively with the other two, PPE and structured encryption. And then you have structured encryption, which is the technology or the crypto primitive that ROKey uses underneath. And it's kind of like this technology that achieves like kind of like the best of both worlds. It has the query strength, it has the performance, and it has the security. And this is really, maybe I didn't stress this enough, but having this diagram that achieves the best of both worlds is extremely important when it comes to real world deployment. Okay, so let's now focus, now that we have, we went over some of the, research question and also some of the primitives that can solve the end-to-end encryption paradigm. Let's focus on Elasticsearch. So how do we even have end-to-end encryption for Elasticsearch? And this is the diagram that we started with when we were working on Elasticsearch. So you have the app, and you have this ROKey client that sits on the trusted boundaries. And then you have the server, as we have seen in the previous slides, that it's composed of the elastic memory and the elastic disk. So the way how ROKey will provide end-to-end encryption to Elasticsearch is by not changing at all the server. The only thing that will be modified is at the client side, which is you have this, think of it as a, as a process. The app can also be modified, of course, if you are designing an app from scratch, to have this RESTful SDK API that we'll be discussing soon. And of course, you will have all of the guarantees that we discussed about, which is the adversary sees nothing from what you do on your data, on your indices, on your data at all. So what is ROKey Safe for Elasticsearch? So it's the simplest way to describe it is a client-side add-on or API. It's not an Elasticsearch fork. So Elasticsearch remains as is. This is something that will add on top of Elasticsearch to provide end-to-end encryption. And really the most appealing part of ROKey for ROKey Safe for Elasticsearch is that it doesn't require server-side changes. As an instance, if you have an Elasticsearch server running, that's fine. You don't need to change it at all. And if you want to have end-to-end encryption, everything you will need to do is really at the client side, is from the app perspective. The client can use its own key management, meaning that you can have, this is, related to crypto. And when we deal with crypto and encryption, you need to have some key material. And the key can be either generated from a password, it can be, using a key from an HSM. And there are so many other, deployment strategies that you can have as well around key management. So let's dig a little bit more on the features from a mapping perspective when it comes to Elasticsearch. So the API provide what we call flexible field selection. What it means is that when you have your Elasticsearch mapping with all of the fields, you might be in a situation where not all the fields are sensitive. For example, and this is just to clarify the concept, let's say that you have a field called timestamp, and you have another field called SSN and another field called, for example, bank account number. So clearly, like, you want to provide some security around the SSN and the bank account number, but not necessarily on the timestamp. So you might decide at some point, okay, let's just make sure that we encrypt and make searchable these two fields, not the third one, which is timestamp. So Safe for Elasticsearch will provide this flexibility to encrypt what you want. And the other fields, of course, can remain in plain text. The other feature, which is the expressiveness. So the current API, which is the client-side API, provide Boolean search. You can perform range search and pattern search, and this is something that we are going to see in the demo later on in this talk. So this client's API is based on standardized cryptography. We use AES with, for example, a 256-bit key. It uses also SHA-256 HMAC, very standard cryptography. But the way how we use them is in the way, it's all in what we call the encrypted search protocol. We use state-of-the-art encrypted search protocol that our co-founder, Sini Kamara, and myself, we have been working for almost 2 decades. So the current status, Safe is for Elasticsearch is available as a private beta release, currently available as a Java RESTful API, and currently being used by a large public fintech company. So for this demo in particular, we will focus on Elasticsearch version 7.2, but this can be also applicable to other versions. So on the top of this slide is probably what you have as your deployment for Elasticsearch. You have the app, you have probably an Elastic REST API that communicates with your Elasticsearch server. So when you want, for example, to use Aroki Safe, you will be, transitioning to the bottom of this slide. On the right side, the Elasticsearch will remain unchanged, meaning the server. You don't need to change anything. The app also doesn't need to change. The only thing that you will change probably is some calls that you will be making to the Safe for Elasticsearch REST API. So what are the currently supported operations that you can use with the client-side Safe API? So you have the traditional, operation on your documents. You can perform an encrypted add, an encrypted get, delete document. You can still perform exact term or terms search. You can, and this is all, of course, on encrypted data. You can perform match search, and for you in the audience, probably you know the syntax of Elasticsearch. Match search, you want to find all documents where a field contains a specific keyword. It's kind of like providing also some full text capabilities. You can perform Boolean search with or and when you want to search multiple, a document that contains multiple keywords. You can perform range search, integer, double, long, float, dates, single format following ISO actually 8601. Nested search, if you want to search for documents within documents, this is also possible. It also supports more expressive kind of search expressiveness, like prefix, suffix, and pattern search. So where you want, as an instance, to find all documents where a field contains a specific pattern. Here, similarly, you can have the nested search operation on top of this prefix, suffix, and pattern search. So you can always, search documents within documents and so on and so forth. So, okay, so let's see this in practice. So for this demo, we are going to show how we can create an index, how we are going to load some documents, and finally perform some search operations, namely Boolean, range, and pattern searches. So let's start with the index creation and loading documents. For this talk, we picked the IMDb dataset, which is like a publicly available dataset. So on the left side, you have the fields that the dataset contain. You have tcons, ordering, ncons, category, job, and characters. Each field has a different data type. For example, ordering is just a number to uniquely identify rows for a given title. So for example, here you might want to perform a range search. And on the other hand, you have, for example, characters, which is a textual field that contains the name of the character played. So on the right side, it actually depicts what the mapping looks like. So you have, many fields that they have simply keyword. And this basically means that you want to perform really one of the simplest search operation, term search. You have ordering, which is an integer, and then you have characters, which is a text, where you want probably to perform prefix, suffix, or pattern search operations. So let's go to the terminal. I will just exit right now the presentation, and we will go to, so let me first maybe show you the data set. The dataset is as follows. So this is the IMDb dataset. If you download it from the IMDb website, it contains documents that they have the following form. So you can see here, like the characters can contain some text, and this is just, we use this dataset for example. So let's go back to Eclipse, and this is what we are going to do. The first thing we do is we want to create an index. So I will just click on run, and this will create an index for us. So let's go to the terminal to check what are the indices that have been created. So here we just send the query to the server to see, okay, tell us the indices that have been created now. So we have created like a plain text index, and this is an index that will serve as a point of comparison. And these are the two indices that have been created, to mimic what you might be doing on a plain text index. So you can already observe that the name of the index is encrypted. So even the name of the index can be encrypted. Of course, you can opt not to encrypt it if you want to. But this demo is going to show you the kind of like the extreme kind of security where you encrypt everything. But of course, you can choose not to encrypt maybe some of the fields, not to encrypt the name of the index as well. So one question that you may ask as well here, okay, why do we create two indices for one? And this is, the answer is related to the crypto primitives we use. So one index will be used to store some crypto information that will be important to perform the search and the updates throughout the life of the index. And the other one basically will hold the encrypted documents. So, okay, let's go back and let's, okay, so before going back, let's check the mappings so you can have an idea of, okay, let's search for the mappings. And let's start with the oops. So this is the mappings of the index, the plain text index that we have created. So you can see these are exactly the fields that we have gone through over on the in the slides. So let's see how these mappings now will look like in the encrypted index. So you can see this is the new mapping that you will have in the encrypted index. So the first observation is that you will have like more fields than the ones that you started with. And this is normal because of how the crypto will work. And the second observation is that the name of the fields are also encrypted. So an adversary, even at this stage, let's say that you don't have anything on your server, you just created the index. Even at this stage, if there is an adversary, it can't infer anything about the structure of your index. Everything is encrypted, even the field names. And just
sorry to interrupt. There was a quick question in the chat. How much additional storage or overhead does encryption add?
Yeah, this is really a very good question. And the answer is really, the correct answer is it depends. It depends on the templates or the number of fields you want to have. It depends on the expressivity you want to perform on a specific field. From a cryptographic standpoint, for example, if you want to perform full text search on a specific field, on most of the fields, then you will end up with more storage than what you would have if you wanted just to perform exact term or exact term search. But to give you an idea about like with the current implementations we have and with the current interaction we had with some of our companies we work with, it can vary from 2x, 2.5x, and it can go in the extreme case when you want to encrypt everything and have full text search to have 15x. But you will have best security in that case. So it varies, it depends. So some templates, the storage overhead will be very minimal, but for some other templates, depending on the search expressiveness, it can go to one order of magnitude and more in terms of storage. Yeah. So yeah, so this is the mapping. So hopefully I have answered your question. Let me know if you have a follow-up. So the mapping, so this is the second point. Just to go back to the second point that I wanted to mention here is that the field names are encrypted, so the adversary will not even know what is the field name is about. Okay. So let's go back now to Eclipse and do some document insertion. So what we will do right now is we will insert some documents. And this is just a script that I have written to insert the documents that we have seen in the IMDb dataset. Oops, this should not go now. Documents insertion. Yep. So we have inserted the plain text documents and now we are inserting the encrypted document. So here in this demo, what we are doing is we are taking the worst case scenario, which is we want to encrypt all the fields and we want to have all the fields depending on the expressiveness that we have mentioned in the slides. So we have inserted one document in the plain text index and we have also inserted one document in the encrypted index. So let's go back to the terminal to see how the documents look like. So in the plain text document, we have so we have mapping. So let me just change that to search. So when I do search here, you have the plain text documents that you have that we have stored. So everything is in clear, and this is something that I want to go back to, which is if there is an adversary who can observe the memory, it can see exactly what I'm seeing here now. Namely, it sees the plain text information of the documents. So imagine now that you have sensitive information, so it can or infer it very quickly, see it very quickly. So now let's do, okay, let's do a search on the encrypted index. And this is what the encrypted documents now look like. So the document is, all the fields are encrypted. So these are, the left side hand is the field, and the right is the content of the field. Everything is encrypted. An adversary cannot infer any information when it's, for example, this data set is breached. So one important thing that I would like also to emphasize here is that some of you might be familiar of PPE or deterministic encryption, where you encrypt the same value deterministically. So when you use, for example, PPE, what you will have is that if you have the same value in two different fields or in two different documents, what you will end up having is that the encryption will look the same. This is really problematic because if I am the adversary and get hold of your data set, so I can just have this massive frequency information based on which I can extract valuable information. And as I have mentioned earlier, this has been shown actually to be feasible, and it can recover in some scenarios up to 100% of the data. So with SCE or structured encryption, you don't have this drawback, you don't have this security problem. What it means is that if you have the same value that it appears in two different documents, the encryption of that value will be different. So here, for example, I have no idea whether this is for the same value or not, because they are encrypted differently. It might be, it might not be. So I don't know as an adversary what is the content of this value. So what we say from a cryptographic standpoint, we say that the structured encryption has a, hides, this frequency. It doesn't disclose this frequency information. So this is what the documents looks like. So let's go back now to the presentation to go over some of the search operations. So the first search operation we will start with is Boolean search. And for those of you who are familiar working with the Java API, RESTful API of Elasticsearch, you might recognize the code on the top of the slide. So basically, these 3 lines are the code that you will need to perform Boolean search on a plain text index. You might need more code, but these are the backbone kind of skeleton of the Boolean search. On the bottom of the slide is actually the equivalent code that you will end up using if you use safe arrow key safe for Elasticsearch. So there are 2 changes. So before talking about the changes, let's talk about the similarities first. First of all, you can see that the skeleton is the same. We have exactly the same number of lines, almost the same, inputs, and almost the same names. So now, okay, what are the differences? The differences are very small. First of all, you need just to make sure that you will start your constructor with the word safe. You need to prepend the constructor name with safe. And this basically means that you are now working in the encrypted realm, not in the plain text one, but just, working on your encrypted index. So this is the first modification. The second modification is, as you can see on the input of Safe Match Query Builder, usually it takes only the field name and the query. But now it takes more than just the field name and the query. It takes the client and the index name. So these 2 additional inputs, they are necessary for the cryptographic operations. What it means is that the client implicitly holds some information related to the cryptographic key or the cryptographic credentials that you need to have in order to perform some encryption and to perform, of course, the encrypted queries and the encrypted, updates, and eventually the decryption as well when you receive your query. So this is very important to have to perform the cryptographic operations. Other than that, all of the other inputs remain the same. So let's go back to the terminal and see how this works. So what we are going to do, we are going to search on the field's character, and we will have the text that we would like to search is himself and Germany, and we want to search for all documents that they contain these 2 values. And we are expected to have just a single hit. So as I mentioned here, we have himself Germany character, and this is the operation that we have. So we will perform the search operation, and this is what we will have. Actually, it's more than just 1 hit because I think that I have put an or, not an and. So for or, not and, you have 4 hits, sorry. And you can see that the hits are the same, either for the plain text match and also for the encrypted index match. So you can observe that we have fetched the identifier 80, 41, 52, and 53, and is actually the same for the plain text search. This is just to show that, the correctness, and also you can also observe how fast the search is for an encrypted plain text search. It's almost seamless. So another thing that I want also to highlight here is that from an application perspective, you will always receive the decrypted documents. So here we have already decrypted the documents for you. So you don't receive the encrypted documents. So the SDK or the client-side API will take care of the decryption of the results as well. So let's go back to the other search operations. So we will have range search, and this is another expressiveness that we know how to support with the current client-side API is when you want to perform greater than, less than some values. And the same remarks we had for the Boolean search also apply for the range search. Namely, you have the same code, except for the safe word that you need to prepend the constructors with, and also like the client and the index name that you need to provide as an additional input. Other than that, all of the code skeleton is the same, which provides really an easy integration and also some seamless integration, I would say, for a developer who would like to use the API. So if you are familiar with Elasticsearch API, you can use this API similarly. So let's go to range search script. You can see here we have the lower bound we want 7, the upper bound of the interval 9, and we are searching the field name ordering. I will run and let's see the results. So I forgot the number of hits, probably 2. Yeah. So we have 2 hits. So here are the 2 hits we have. You can observe that the ordering is 8 and 7. This is exactly what we wanted. And for the encrypted range search, we have also 8 and 7, and this is exactly what we want. And finally, let's go back to the final search operation, which is pattern search. And pattern search, if you are familiar with Elasticsearch, we use the query string query builder. And if you want to search for to have more expressiveness in the query. So here it's almost the same. It's a little bit even simpler with Safe for Elasticsearch in the sense that you need to specify the field name inside of the construction. But there is the same, basically the same differences. You need just to prepend the constructor with Safe and make sure that you give the correct input information. And here we are going to search for characters, and we have this pattern, which is self. So the number of hits is 16. We won't be able to go over all of them. Okay, so pattern search. Yeah, so let me just modify this one. I said self characters. And let's run this. Let me see. So the maximum response is 5. So we just limited the maximum results to 5. So we still have 16, and the same thing happens. It's really seamless and it's fast. So we get all of the results we want, and they are all decrypted. And you can observe that if we go to characters, you will see that it contains the self that we wanted for both the encrypted or the plain text. So we actually fetched what we wanted to fetch.